This video is going to cover the topic of compound events with unequal outcomes. Be sure the date and topic are at the top of your page. The essential question for the video today is, how do we determine the likelihood of compound events when there are unequal outcomes? Up to this point, we've been looking at compound events with equal outcomes, right? Heads or tails is an equal outcome, or a spinner where all the sections are equal. But let's take a look at something a little different. Let's take a look at spinner 1. You can see from the spinner that one section is much more likely than the other, and I'm going to record this in my probability model. So the chance of landing in red is 1/2, the chance of blue and green are both 1/4, and I know if I add that up, it equals 1 whole, which means it is a valid model. On the second spinner, both of these sections are equal. So again, let me make a quick probability model here, a valid probability model. And since each yellow and gray take up 1/2 of the space, I know that the probability of getting either one is 1/2, which adds up to 1, and so it's a nice valid model. So the question is, what's the probability of me spinning a red, right, a red on the first one, and a yellow on the second one? This might be something that could be useful for a carnival game, for example. Well, I'll start by setting up a tree diagram. That's my favorite of the options, so I'm just going to go ahead and do that on my next page. So here I've started my tree. I know on the first spin I can get a red, a blue, or a green. And of course, following that on spin 2, we can either get a yellow or a gray. Right? So it looks like we have 1, 2, 3, 4, 5, 6 different outcomes, 6 possible different combinations. However, right, we're looking for red with yellow, right? This is not simply 1 out of 6, right? There certainly are 6 options, and this is one of them, but there's a greater chance that I'll get a red on my first spin because it's a larger space than all the others, right? The outcomes in these are not all equal. But I do know that if I look at the probabilities of each step, I can use that to find my total probability. So let's fill some things in here. I know that my red spin, I have a 1/2 chance of getting a red. I have a 1/4 of a chance, 1 out of 4 chance of getting blue, and the same for green, right? That's from our probability model earlier on. When I spin my yellow and gray spinner, I can have a 1/2 chance of getting yellow, 1/2 chance of getting gray on each of these branches, right? Anytime I spin that second spinner, I have a 1/2 chance of getting that. So let's look at the path that I'm wanting, right? I want red with yellow, and I have a 1/2 chance of getting red, and then from that, of that turn, I then have a 1/2 chance of getting yellow. So my probability is actually 1/2 of the 1/2, and that means it's 1/4. I have a 1 out of 4 chance of getting that red-yellow combination. 25% chance of getting a red and a yellow. Of course, let's just do another spinner example again, because that's a nice kind of visual example that we can use to prove our point or to kind of practice our point here. Okay, so we have our 2 spinners, and maybe we're trying to figure out the probability of getting a blue on both spinners, right? That's the only color that would match, so maybe we're trying to see if we can get a match. And obviously on the first one, once again, these are all nice equal pieces. They're all 1/3. But on our second spinner, right, this pinkish color takes up 1/2 of the space, while all of these other sections here only take up 1/8 of the entire spinner, right? So if I was making my probability model, I'd have that all written out, and I would double check that, of course, those add up to 1 whole. So if I'm trying to figure out the probability of getting blue and blue, I'll do a quick little diagram. And after I spin my red, my blue, or my green, I'm going to spin again and either get gray, black, yellow, blue, or pink. So I have my tree here, and remember, I'm trying to get blue, blue. So what I'm looking for is this blue, blue combination. And you might be tempted to say, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 outcomes. But of course, that doesn't take into account that some of this is more likely than others, right? You're far more likely to get pink on this turn than anything else, right? So instead, I can think to myself, well, I have a 1/3 chance of getting blue the first time, and then I only have another eighth of a chance, I'm going to squeeze that in here, an eighth of a chance of getting blue the second time. So I have 1/3 the first time, and then of that, I have a 1/8 chance of getting it the next time, which means I have a 1 in 24 chance of actually winning this game if I had to get a matching blue. So it's not very likely that that would happen. And we'll see more examples of this when we work on it in class, and this will be particularly valuable as you're trying to think about carnival games and how you might set up a game that might be more or less likely for a patron to win or lose. So remember, this essential question was about determining the likelihood of compound events when there are unequal outcomes, for example with a spinner, like we've seen here, where the spaces are not all the same size and therefore not all equally likely. Be sure to bring your notes and have any questions in class.